Hello everyone, thanks for joining me. I'm Noah Wahlberger. We're talking about physics and relativity. Today I'm going to interject a video about definitions in physics, and I want to discuss the interesting parallels that I think there are between foundational issues in physics in the definitional direction and also foundational problems in pure mathematics in the definitional direction. There's curiously a kind of parallel between these two. And today we're going to focus on an important historical figure named Ernst Mach, who was an Austrian physicist and philosopher and quite influential in Einstein's thinking. He was somebody who thought a lot about the role of definitions in physics. How do we actually go about specifying clearly what the various concepts that we're using actually mean? And his approach was that definitions should really correlate with observational measurements, a kind of down-to-earth or empirical approach to this subject, which I have a lot of sympathy with, as we'll see. So he wrote a couple of influential books, Science of Mechanics and Analysis of Sensations. One of his guiding ideas was what called the principle of economy, that scientific theories should be as simple as possible. And he also advocated skepticism towards concepts which are not directly linked to observation. So he wanted to sort of separate physics from metaphysics, and a concept is metaphysical if we can't actually pin it down explicitly and concretely to something we can measure. That was his approach, and it was quite a convincing approach and very influential. So Mach insisted that scientific concepts ought to be defined in terms of operations that specify how they are measured. If you want to define the quibble of a particle, then you should not talk in terms of abstract things, but the quibble is, something out there and which is a little bit hard to describe. Rather, you should say a quibble is what you get when you measure this and this aspect of that particle in this such and such a fashion, and may perhaps make the following computations. The number that you get will be called the quibble of the particle under this certain circumstances. Okay, something like that. So there are a number of foundational concepts in physics which we're all familiar with from high school, and they are introduced in a kind of informal kind of fashion, and we end up working with them in explicit situations, and so we sort of end up getting an intuitive understanding. But when we actually come about trying to understand what exactly these concepts are, then it becomes much more problematic. And this is where Mach's point of view becomes relevant, because we have to ask ourselves, well, what actual observations should we really adjoin to these various concepts, and in what fashion? So key examples that play a big role, of course, in relativity and quantum mechanics are mass, force, energy, momentum, position, velocity, acceleration. So each of these concepts we have an intuitive understanding of. Mass is perhaps the amount of matter. That's what people used to think, amount of matter in an object. Force, well, it's a kind of a pushing or a pulling, sort of, but what actually do you need to measure in order to be able to say, aha, here we have a force? Energy, momentum, position, velocity, acceleration, these ones here are all thrown into question, really, by Galileo's invariance principle, because Galileo, as we've seen before, advocates the idea that it's impossible for us to define the notion of stationary. Hence, it's impossible for us to ascribe an absolute velocity to anything or an absolute position to anything. So these concepts here are immediately suspect from the Galilean point of view. And if position and velocity are suspect, then you have to also ask, well, if you're going to define acceleration in terms of velocity, and velocity is not properly defined, then there's a problem with acceleration. If you're going to define energy or momentum in terms of velocity and mass, and these ones here are already problematic, then these ones here are going to be problematic too. So basically all or much of sort of high school physics comes into question when we adopt Mach's principle here and ask, well, what exactly are these objects? How can we define them exactly? And moreover, how can we do so in a way that's consistent with Galileo's invariance principle. Now, the concept of mass is particularly interesting because it has these various incarnations, and over the last 200 years, it's actually morphed in its meaning in very considerable fashions. Now, if we go back historically, well, the ancient Greeks had a notion in that direction, but they didn't really have a notion of mass. So Aristotle talked about heaviness and lightness of things, and there's certain types of materials like earth, wind, and fire, etc. Archimedes got pretty close to the concept because he was interested in density of materials, with his buoyancy principle and with this problem of weighing the king's crown to see if it was made of pure gold. Galileo was also thinking about mass in terms of inertia, in terms of the resistance to an acceleration. And then we get to Newton, whose laws of motion, as laid out in the Principia, have mass as a central concept. Although I think it's fair to say that Newton doesn't really pin down exactly what mass actually really is. So during that time, there was certainly this distinction between inertial mass. So you have some force acting on something and it creates an acceleration. And the mass is some kind of proportionality constant between the force and the acceleration. So as embodied by Newton's second law, F equals ma. So there's that kind of inertial mass. But then there's a slightly different role of mass in Newton's law of gravitation, where we have the gravitational attraction between two masses, but it's not obvious that the masses that are occurring in that law are really the same as the inertial masses. And the ones associated with gravitational mass, well, that's more close to our familiar notion of weight. And of course, most people in practice just identify mass with weight. They're almost synonymous as far as most practical people are concerned. But of course, in physics, we realize that there's actually an important distinction between these things, that the weight is just the force that a mass feels due to the Earth that we happen to be on. So I think the general feeling was that mass was some kind of reflection of the amount of matter. You just sort of count up how much stuff there is. But this is before the atomic theory was really developed, and when we realized that there were atoms, but some atoms were more massive than others. So it wasn't just a question of counting. So I guess the standard notion of inertial mass is the resistance to acceleration when a force is applied. And then in the 20th century, when Einstein comes along, then mass ends up having a more complicated aspect. There's then a concept of relativistic mass was introduced, and in fact that ended up playing an important role, and then it somehow sort of receded from the discussion as physicists perhaps changed their mind as to the role of relativistic mass. So I think nowadays relativistic mass is not given the importance that it used to have, okay? So there's been some shift in this direction. And of course, Einstein's famous equation E equals mc squared more or less identifies mass with energy. So then we have, a completely new way of thinking about mass as it basically embodying energy. Now, there's another kind of mass which I think is usually not discussed, but I think it's actually important to add this to this already rather extensive list of ways of thinking about mass, and that's what we might call scattering mass. And this is actually what physicists use in accelerators and cloud chambers and such. So you slam two particles together, and then there's some resulting collision and scattering, and we measure these various directions that are emerging here. And in some situations, we can then make some statements about, given conservation of mass and perhaps conservation of energy. We can make some statement about the masses of the various constituent particles. Okay, and it's also worth saying that in this kind of context, it's not really an absolute mass which is being involved, but rather a ratio of masses. So this is an additional complication that comes about in physics in a lot of different contexts, where actually effectively, when you actually think about what you're actually measuring, you realize that it's really the ratio of two things that you're actually registering. It's not an absolute thing, it's rather a ratio. So we're going to have to talk more about that. So we're really going back to the ancient Greeks, really. and their discussion of proportion in the context of geometry. That's perhaps the relevant concept for a lot of physics here. But in any case, there's a kind of a mass that's occurring in scattering here, which perhaps you could argue is the same as inertial mass, but I don't really understand that argument. To me, this is sort of a separate kind of alternative way of thinking about what mass is. And in fact, to me, this is quite a fundamental way of thinking about it. And then in more modern times, we have this, remarkable thing which you will have heard about, that, well, we have quantum fields, and we have the standard model of particle physics, and prominent in the standard model is the Higgs boson, which was discovered 10 years ago or so. And so there's this Higgs field, and you've probably heard the statement that the Higgs field is what gives mass to the other particles. Now, that's a statement that really sets one aback when one hears it, because, what does that mean? I mean, so suddenly we have to take all these prior existing notions of mass and somehow put them on a shelf, and now we have a new way of thinking about mass coming from this remarkable particle, which was only discovered 10 years ago and about which we don't really know all that much in some sense. Okay, so, and even the meaning of that statement, what does it mean for the Higgs field to give mass to particles? I mean, is something that I don't understand, and I'm not sure if I've heard physicists clarify, what actually the meaning of that is so clearly. But anyway, so we see that even a notion as seemingly elementary as mass actually has a lot of complication to it. And so Ernst Mach would say, okay, it's a lot of complication, so what you need to do is you need to decide on one of these things, and then you need to anchor your definition by saying, what exactly are you going to measure? What exactly are you going to measure in order to get the mass of something? And until you've made that kind of connection between this abstract notion and a specific measurement, you don't really know what you're talking about. So I think one of the reasons why the public generally finds discussions of relativity difficult to really understand, despite the cute little pictures of spaceships going this way and that way, and light beams bouncing back and forth, is that there's a sense that we're talking about things which haven't actually been pinned down in a really solid way. And I think that a lot of expositions of special relativity really do suffer from this weakness. And unfortunately, I see a great parallel between those, we might say, definitional confusions in physics and corresponding definitional confusions in mathematics, in particular in pure mathematics. So it turns out that there is very great similarity between some of the issues involved here. That in mathematics also we do the same kind of thing. We have some concepts which we sort of have some prior intuition for, in maybe that we've developed in high school. And then we just sort of, take those intuitions and we slap on some kind of formal definitions, sort of like after the fact definitions, that don't really, they're not really proper definitions. They're sort of makeshift definitions that make it look like we have, a proper foundation for this concept. But what we're really doing is we're just relying on that prior intuition that we hopefully gained during our high school years. So examples of that are number. That's a key one. Number, function, geometrical things like curve, length, manifold, more complicated, variety, topological space. So there's a whole host of these things. But a lot of them, in fact, all of these, in my view, suffer from this basically not taking the role of the definitions seriously enough, right? That if we really stop and examine this concept in a critical kind of fashion, and first of all insist that why don't we start with defining these things exactly, and then we should to anchor our definitions, we should actually have examples so that we can see, that this definition that we've just introduced here can be expressed, can be shown, can be demonstrated with this example over here. Okay, so that's a key problem in pure mathematics. And curiously, the length one is particularly interesting because the concept of length and the concept of distance, those are basically the same kinds of things. So both physics and pure mathematics suppose that the notion of length is almost God-given. Like everybody knows what length is. You know, this thing is a foot, let's say. Well, everybody, we don't need to say what that means. Everybody knows what that means. Look, it's a ruler, it's a foot, whatever. But it turns out that in physics, if you want to define length, well, you have to talk about coordinate systems. You have to worry about motions. You have to perhaps fuss around about, you know, is there going to be a difference in measurement between different observers going in different directions? Correspondingly, in mathematics, you have to worry about, you know, what's the actual rule that you're going to use to get the length between, say, 2 points in the plane. If your rule is going to involve a square root, like it usually does, right, then you have to fuss around about, well, can we actually calculate the square root? I mean, if we can't calculate the square root, then the formula for a length involving a square root is ultimately a wrong formula, okay? And so it's interesting that there's a parallel there. Okay, so corresponding to Mach, I insist that mathematical concepts ought to be defined in terms of procedures that specify how they are expressed. So for me, if you take one of these concepts, a function, it's not enough to say, oh, a function is a rule that blah, 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 and then you spout some phrase, you know, that perhaps has some meaning to you and somebody else has quite a different meaning. Rather, I want a procedure. Oh, you will have a function. Okay, so there's a procedure then that you are going to initiate that will end up you writing something down on a page, you expressing something. Okay, so that you end up with some stuff on the page, and then you can show the page and say, this is the function. And whatever criterion that the function ought to satisfy, we can check that what you've written down satisfies that criterion. Right? That's a kind of a Machian analog in some fashion in pure mathematics, that we want to anchor our definitions by explicit expressions that can be written down so we can compare, so that we can see things in their entirety, not just, you know, floating in some abstract world of pure thought. Like, oh, consider a real number. Okay, if you have a notion of a real number, what do you actually have to write down on a piece of paper to specify a real number? Right? Once you ask that question, once you make that demand, then, you know, analysis basically crumbles, sadly, okay, because they can't do that. There's no procedure for actually explicitly on a page performing the operations of arithmetic. So the whole thing is a sham in some kind of subtle way, even though it's approximated by the finite decimal kind of arithmetic that the engineers and the physicists use. But they're requiring something different. They don't require infinite decimals. They do not say, oh, we need to write down an infinite decimal. They'll say, no, you need to write down 5 decimal points or 10 decimal points, whatever. You know, and take care of the imprecision involved in maybe a truncation or round off that you've made. So I think this is pretty interesting, and it's very relevant for our discussion going forward on special relativity and quantum mechanics ultimately. So we want to always keep in mind this prescription of Ernst Mach that, you know, really, if we're going to be honest, if we're going to be careful, if we want to really understand the world, then we should make sure that before we start having elaborate theories, that our foundational notions are clearly laid out and pegged to observational, empirical reality. I'm Norman Wildberger. Thanks for listening.